I'm Cyrus, and talk to everyone today about my work in autonomous vehicles and predictions, making them interpretable in that area. So in the US alone, over 3 trillion miles are driven each year. So what if there's no need to be at the wheel? One of these could be shared rides. There might be many fewer vehicles on the roads, not to mention the increased access to mobility. So one aspect of human driving that autonomous vehicles have yet to fully replicate are interactions. And here we see one vehicle having difficulty with merging. And humans have little trouble with this, and as well as other more complicated scenarios, such as navigating among pedestrians. So how might this be achieved for autonomous vehicles? So I'll tell you how autonomous vehicles work and the pipeline there from a prediction-centric view. So the first step in this process is that the vehicle will sense its surroundings, lane boundary signs, and where other fellow road users are in the world. The prediction system will then take this information, the observations of, say, where others are, where they are in relation to the road or other signs, and predict their future movement. The control system then takes this information to formulate constraints for safe driving within lane boundaries and to avoid collisions with other road users to navigate a safe course. So predictions of how fellow road users behave guide the autonomous vehicle's interactions. So specifying how predictions are made specifies a large part of the autonomous vehicle's behavior. So to predict how interactions between participants on the road affect future motion, one possible and effective approach is to collect a data set full of interactions of people driving on the roads and interacting with each other. And this can be used to train and learn a model in a model-free framework to make predictions. So this can achieve great accuracy, being fully data-driven. But this may make the predictions and in turn, the vehicle's behavior less interpretable. So the goal of this work is to support transparent and predictable vehicle behavior and to build interpretable models of interactions to make predictions. So how do we build such a prediction model and what might be some desirable elements? So first, we do want data to see road users' interactions and how people actually behave. But we can't have data just alone. To be able to use this data, to be able to calibrate the model's predictions to what is actually observed in the data, we would want a fitting procedure to do this calibration. So having both parts is key in model building. So if these two parts form the piece of model building for prediction systems, what about actually using the predictions, making them? So next we turn to inference, which is the problem of making predictions. So these prediction methods are also for real moving vehicles. So should a pedestrian suddenly appear from behind a parked vehicle, real-time speed is of the essence to quickly adapt to changing surroundings. And with imperfect sensing, where road users may only be suddenly or sporadically detected, robustness to missing data is another key feature. So next, in the scene, even if this patch of road in the front near the pedestrian is marked as a crosswalk, or there's a stop sign, whatever the environment, we want the model to predict accurately. So model generality is the last main feature of focus here. So the first contribution focuses on the data aspect of model building, develop a novel simulation framework for when labeled data is scarce or the cost of getting it are high. So of the available prediction models, time series models are common, but these have difficulty incorporating semantic data, such as data of where the sidewalk or the road or the crosswalk are, and social data. So if we want to predict how multiple pedestrians may be interacting with each other as they're walking. And these also rely on hand-chosen features, which can hinder generality. Inverse optimal control has allowed the incorporation of high-dimensional semantic data. So we have an image here, and we can see that the predictions made by this work has predicted that the person is more likely to walk on the sidewalk rather than cutting through the parking lot. But these methods do not scale well with the number of pedestrians. And more recently, neural networks, or deep neural networks, offer a flexible framework for handling both semantic and social data. But these too have their downsides. So besides focusing less on interpretability compared to classical models, which have tens of parameters to learn, neural nets typically have thousands to millions of parameters. And for this, we would like correspondingly large amounts of labeled data. But to get such data, this often entails a vast manually labeling effort, which is very costly in both time and labor. So sensors offer another approach to try and automatically label this data. And so we have here a mocap system, which will automatically record the positions of these people. But this controlled laboratory environment will probably not get us the representative data. So here, what is proposed is a framework to leverage just a small, easily collectible amount of data and use this for sampling to then generate a large synthetic data set, which can then be used to train a deep neural network for trajectory prediction. So for related works, simulation has been used to train state-of-the-art neural networks for object detection using simulated data alone, as well as other things such as modeling forces for grasping. But it is better suited to modeling physical phenomena, such as lighting and friction, rather than pedestrian behavior, which does not follow a set law. Instead, the next approach is leverage some amount of existing real data to overcome the limitations of simulation. So data augmentation is another technique, and it uses label preserving transforms to generate the data, new data from the old, based on symmetries in the data. So here we have an image, and its label is cat. So if we flip this image, it's the flipped image, but its label is still cat. So this flipping can be used to create new data. And it's been widely applied in image classification and object detection, say for detecting pedestrians, and other fields, such as acoustic modeling, but has not been applied to pedestrian trajectories. And the proposed method is most similar to data augmentation, where we use a combination of transforms and sampling to generate new data. We also have generative adversarial networks, which learn a generative model to create realistic samples. So for pedestrian trajectories, they've been used for a given initial segment of a trajectory to try and create a realistic future segment as the prediction that cannot be distinguished from the real data. And we show that this state-of-the-art network still benefits from the proposed framework. So for our problem statement, our setting is that given some number of pedestrians, we have, there we go. We have some number of pedestrians, and we're given their observed positions in the 2D top-down plane. So observing their positions, say at the first time and at the next time, we observe it for a number of time steps. The goal is to predict where they will be in the future. And for sampling, our goal is to generate these positions for training. So for a sampling framework, the first step is to sample the number of pedestrians in a batch of data. And so for each of these pedestrians, then simulate a trajectory, which consists of a path, which has no time information, just a sequence of positions, and speed, which tells us when each of those positions comes true. And from this, we can obtain the trajectory. So having sampled the trajectories for one batch of pedestrians, we can repeat this many times to simulate many batches to create a large synthetic data set. So the first step is to sample the number of pedestrians in a batch based on the mean and variance pedestrians at any given time in the real data set. And to sample paths for each of these pedestrians, we first look at the data as one trajectory for each unique pedestrian in the data set. And then for each trajectory, we introduce a distribution over which other likely trajectories may be found based on perturbations. So if this is the original trajectory, to perturb the trajectories, we can consider a small translation in the 2D plane. So the idea is that the pedestrian's motion itself is what is likely, and if they started from a slightly shifted position, the motion is equally likely. We can also consider reversal, as if the pedestrian had walked the opposite direction. And a truncation, as if the pedestrian had been recorded starting from a different time. So having defined this, we can sample from the distribution induced over the entire real data set and sample one trajectory. And we can do this by sampling uniformly from the data set and then perturbing one. And then to this perturbed trajectory, we need to fit a piecewise linear spline parameterized by distance. So this spline gives us the path, which has no time information. Now, to associate time information to that path, we need to sample the speed. And here, each pedestrian is assumed to move at a desired constant speed. And around each speed, we assume perturbations are distributed normally to that speed. So then to sample, we can sample from the resulting mixture distribution. So to evaluate this framework, here the tests are conducted on 2 pedestrian data sets, each having 2 scenes. So here, one is picked as the test data set, which is not seen and reserved for testing, and the remaining are used for training to build the deep neural network prediction model. And this is repeated for all combinations. So the different methods that are compared, the first is just training directly on the real data, as we would normally. Just training directly on all the real data that we have there. The next is to use the proposed framework to use the real data and generate a very large synthetic data set and train the deep neural network on this large synthetic data set, and then use it to make predictions. And now, to control for the number of labeled frames of data generated, we next generate a synthetic data set with number of labeled frames equal to that of the real data. And lastly, also compared is training on the combined data set of the real and the large synthetic data set. And now, to simulate, what if there's only a very small amount of real data that was labeled? To do that, we can take 20% of each labeled data set and treat it as if it were the actual data set, and then repeat this entire procedure. So for evaluation metrics, we have X that denotes the position, the actual position of the pedestrian, and X hat denotes the prediction. And this is a random variable because the prediction method is probabilistic. So for that, we draw 100 samples. and we examine the metrics, the average distance error, which is the average distance that a prediction is to the actual position of the pedestrian. We also consider the minimum distance error, which is the distance of the closest prediction to the actual position. And lastly, the final displacement error, which measures the average distance at the final point of the time horizon. So comparing the method trained on the real data to the method trained on a large synthetic data set, we see that the errors greatly decrease. And so that the synthetic data here lowers errors. Now, controlling for the number of label frames of data that are generated, we see that training on the larger data set of synthetic data achieves lower errors, so that more synthetic data helps. So now comparing training on the combined data set to the large synthetic data set, we see that there's not a great difference between the two. And this makes sense because the synthetic data was built using real data, so the real data may be redundant because it contains the same information. And so the deep neural network does not learn anything new from additionally seeing the real data. So to see some qualitative results next, here are the predictions on the ETH dataset. So we want the predictions shown in blue made by each method trained on the real data on top and the large synthetic dataset on bottom. We want the predictions made for the pedestrian that walked along the green trajectory to lie on the end of the orange trajectory that they walk in the future. And so as time progresses, we see that the predictions scatter due to uncertainty as it's predicting further out in time. But as that happens, the method trained on the synthetic data yields predictions that are centered around the pedestrian, unlike that of the one trained on real data. And in this example, training on the synthetic data yields predictions that are more tightly clustered around the pedestrian. So with this framework, we've seen that synthetic data helps combat overfitting, and that more synthetic data helps, and that this is effective with both small and larger amounts of real data, so that deep neural networks can be applied to settings with limited data or where the cost of obtaining data are high. So this work focused on making a framework to improve prediction methods, and the next focus is on building an interpretable model for the setting of highway driving interactions. So here, the focus is on ramp merging due to the time constraints that make quickly obtaining the predictions even more important. So highway ramp merging is one common scenario in highway driving. And the typical pipeline that an autonomous vehicle will use is to first collect observations of other vehicles and use these observations of where they were to predict where they will be in the future. So if this is the view at the start, collecting observations with the traditional methods, the next view then looks like this. But all the vehicles have moved, and we have much less time available to complete the merge because 3 whole seconds have elapsed. And this is because traditional methods assume that we can collect observations for 3 to 5 seconds before making the first predictions. And so what if instead of using this long window, we could instead use a very short window, just see a few observations before quickly making predictions. So if we did this instead, we'd have much more time left to actually make the predictions and to execute the merging. So we focus on the case of ramp merging to these challenging time constraints. So for an overview of the method, here we start from a deterministic car flow model to describe the rear or lag vehicle's longitudinal behavior based on its interactions with the lead vehicle it's following. And this is then extended to probabilistic setting, so that the autonomous vehicle can better adapt its predictions to the lag vehicle's behavior and merge onto the highway. So for this method, first observing positions over standard size windows of 3 seconds or very constrained windows of 400 milliseconds worth of data. Method then fits the probabilistic model to the data with a novel and real-time consistent inference procedure. So this initial estimate is then used to sample predictions. So in previous works, simple kinematic models are one extreme, which need few observations, but model no interactions. And this may be important when vehicles are maybe slowing down or making sure that a gap is only a certain size between them. And so models that focus specifically on interactions have used manually defined cost functions that define behaviors. But the majority of research have focused on deep neural networks, which have proven the most successful. And these methods all account for interactions. But aside from focusing less on interpretability, they typically assume large observation windows of 3 to 5 seconds. And next, we also have car following models, which comprise a set of kinematic models focused on balancing the need to account for interactions, on one hand, and on the other, the need for prediction with few observations. But many of these models rely on manually specified parameters, which can make them less responsive to individual drivers' behaviors. So to define the model here, we define the state space, which is the position and velocity for each of the vehicles, the lag vehicle that we want to predict, and the lead vehicle that it is following. And then based on this, Wei et al. Introduced a car following model that's deterministic and we aim to extend. So this deterministic car following model looks at the gap maintained by the lag vehicle. And so this model is defined in terms of several parameters that define how the acceleration of the lag vehicle is chosen. And so its acceleration control is given by 2 terms. One that aims to match the speed of the lead vehicle, and the other which aims to maintain a desired distance from the lead vehicle. So in the probabilistic method proposed here, rather than choosing these parameters by hand, we can develop a real-time and consistent inference procedure to estimate these from observations. So first, how do we fit the car following model? So the first is to fit the observed accelerations so that those predicted by the model based on the parameters match those, the a hats that are observed, the accelerations. And next, in translating this to the probabilistic setting, we add regularization terms to ensure reasonable behavior. And so this term right here specifies the prior belief that the desired gap of the lag vehicle is near the observed values of the gaps that were taken. So the desired gap, G star, is near G0, which we take G0 to be the mean of the observed gaps. We also want that if the lead vehicle is very far away, maybe less likely that the lag vehicle is actually paying close attention to it because it's so far away. And lastly, a chi term, so an indicator function to ensure the predictions with negative velocities over the time horizon are not assigned weight. So this term may be highly non-convex in terms of the parameters theta. So instead of trying to solve this maximum likelihood estimate of theta based on this function f here, we instead examine an approximation without this chi term. So we instead solve this problem. So theta, which is the different k terms and the g star, and we aim to solve this minimization. And looking at the unknown terms, we have this term here, we have terms multiplying each other that are unknown. So it means that this part makes this problem non-convex. And so if it's non-convex, this might be very difficult because it might take a very slow solver to solve for this. But instead, what we can do is use a convex relaxation to solve this much faster. And so using this convex relaxation, we can solve this convex relaxation, get an initial estimate, and then use importance sampling about this for consistency. So this method is tested on the NGSM highway traffic dataset, which is highways from California. So we extract rent merge scenarios from each of the 2 freeways in the dataset. And for baselines, we compare it to the constant velocity model, which doesn't take into account interactions, and the intelligent driver-based method, which is a car following model, parameterized based on the identified lead vehicle, as well as comparing to state-of-the-art deep neural networks. And as an ablation study, we can also compare to what if we use the proposed method, but only used the data fitting term and didn't use the regularization terms. So we can see the benefit or negative part of adding those terms. So if this is an overhead view of vehicles on the freeway, and this is the ego vehicle sensing other vehicles, then the deep neural networks traditionally use observations of all the vehicles on the highway, assuming that all their positions are perfectly known. But more realistically, occlusions and lower sensor resolution at farther ranges may prevent the autonomous vehicle from reliably detecting and tracking farther vehicles. So we also compare to this scenario with restricted observations. And so the deep neural networks that only make predictions for these restricted observations, as Kinematic, are denoted without the star. And for comparison, standard car following models, like the proposed method, only require observations of the target vehicle we want to predict and its lead vehicle. So for evaluation, we also compute for accuracy the root mean squared error, which measures the squared error between the actual position of the vehicle and the predicted positions, and as before, the average distance error. So comparing the different methods on the standard observation windows, 3.2 seconds, the deep learning methods that have access to observations of all the vehicles on the freeway greatly outperform the other methods. And even with observations restricted to the more realistic set of vehicles, they still outperform the basic model that does not account for interactions. And the proposed method, with only the data fit term, performs worse than the deep neural networks. But adding the additional terms, the proposed method outperforms the other methods. So now comparing what happens if we shrink this observation window down to 400 milliseconds. And in this case, the proposed method retained its performance. So now to see qualitative results on the 3-second window scenario, on the left we have the observed positions of the lead and lag pair over the window. And on the right, predictions for each other method over time, with the other methods that use additional observations also seeing those vehicles. And ideally, the predictions should contain the vehicle's trajectory with the red crosses. So in typical predictions, social GAN makes dispersed predictions, but it contains the vehicle at each time step. And MATF makes highly confident predictions, but these drift from the actual vehicle at later time steps, while the proposed method is closer to SGAN. Oops. And in the next scenario, we'll see that here a similar thing happens, but the proposed method has tighter predictions around the actual position than SGAN. And now comparing the speed of each method for making the predictions after collecting observations. Only constant velocity and the proposed method can run in real time. So from this, we've seen that extending the deterministic car flowing model to the probabilistic setting enabled it to adapt to each driver's behavior. And this achieved robustness to very limited observation windows. And in addition, the developed inference procedure based on a convex relaxation aided in making the inference, making the predictions real time. So this work extended that car following model to the probabilistic setting, but it didn't consider lane changes. It also assumes that the leader vehicle is unknown, which might not be the case when in some ambiguous situations where multiple vehicles may be merging in and out of lanes. So the next focus is to improve upon these limitations. So in addition to handling more general scenarios, one of the aims is to also handle more general patterns of missing data. So a vehicle may be seen, occluded by others, and seen again. And this missing data can still be handled. So the previous method and other car following models do not consider motions between lanes. And the kinematic models that can are the simple kinematic models that do not consider interactions, and lane change models that still don't consider interactions. So the aim here is to build a model for interactions that may take place even during maneuvers. So to outline the method graphically, the first idea is based on Bayesian model averaging. So this helps to build a model out of pairwise interactions. So looking at a single vehicle as the lead, we can make predictions. And so extending the idea of the lead vehicle to nearby vehicles, we can make predictions again with this different lead. So now with Bayesian model averaging, we can use that and to combine the predictions. And this provides a way to distinguish the main interactions taking place. So the next part is to specify the model for the lane change and car following. And as in the previous work, relying free parameters to adapt this observed behavior, or adapt to the observed behavior seen in each individual driver. So the next idea here is to decouple longitudinal and lateral motion to model these different behaviors at the same time. So with the lateral, to model lane change behavior, and with the longitudinal, modeling car following behavior. And here, H is modeled as a double integrator. So state is given by the position and velocity along that component. And then a control law is specified for each. So first, lateral motion depends on the lateral target. So where we want to go in the desired lane. So this is unknown, but it's based on the desired lane center line. And it also depends on a lane change horizon. So how fast we want to get to the other lane, which is also treated as unknown. And finally, a lane keeping horizon, which is after the lane change is complete, the vehicle switches to a fixed horizon for lane keeping. So to solve for the actual control, the aim is to minimize accelerations over the time horizon and to reach the lateral target. And we can note that given that the horizon is known, that this control can be solved for in closed form and is linear in the unknown lateral target. And to solve for the longitudinal control, it is based on the desired gap in velocity as in the earlier work. And unlike lateral motion, the horizon here is fixed. So this control is linear in the unknown gap, G star, and desired velocity, V star. So how are the unknown lead vehicles handled? So the vehicle's field of view is modeled over each lane to specify possible lead vehicles. And then integrating over lane, lead, and lane change horizon combinations, the estimation problem is then linear in the remaining parameters, which can then be solved with standard filtering, which will also handle missing data. So for evaluation, this is done from a bird's eye view, where all vehicles are perfectly observed, as well as driver's view, where simplified raycasting is used to determine if vehicles are occluded, in addition to using a sensor range that is limited. So evaluating on NGSIM, the California Highway Traffic Dataset, from a bird's eye view, we have the root mean squared and average distance metrics. And along with those is a quantile-based metric, which is similar to the minimum distance metric earlier. And the proposed method achieves better accuracy on the quantile than the average metrics, but it's not as good, especially compared to the deep neural networks here. But when sensing is limited, it is more competitive. Now comparing on high D, which is a set of German highways, the method achieves good performance under all metrics and retains this performance even when sensing is limited. So to look at some qualitative results now, on NGSIM in the bird's eye view, we have the true trajectory shown in black for the entire prediction horizon, and the true position shown in white with the corresponding predictions at 3, 4, and 5 seconds into the future. And the proposed method here predicts that the target vehicle slows down as another vehicle merges in front of it. And here, the method STLSTM and the proposed method both predict that the vehicle merges lanes. So here, starting from a car following model, but with an unknown lead vehicle, model averaging, or the Bayesian model averaging, provides a means to infer among the possible interactions, like which vehicle might be acting most of the lead. And this helps generalize to challenging scenarios where the lead vehicle is ambiguous. Coupling this with a novel controller enabled handling of missing data. And the structure is also used to drive tractable inference procedure. So the work so far have focused on describing behaviors on highways. So what about pedestrians? And what about in varied environments and possibly interacting with drivers? So the focus is on these questions next. So the key ingredients for standard model-based pedestrian prediction, you need some pedestrians that we want to make predictions for, as well as possibly some number of vehicles. And so the works in this area leverage infrastructure, such as curbs, or mark crosswalks to help determine where the pedestrian might cross, or even facilities at signalized intersections. But in this shared space, there's no sidewalks. And while there may be curbs, pedestrians behave very differently. And our goal is to then extend this line of work to scenes that lack these traditional traffic devices. And outside of shared spaces too, generality is key, since not all crosswalks are marked, and pedestrian behavior may also change across scenes, and they may violate traffic rules. So for an overview of the method, here we have a pedestrian whose observed trajectory has been marked in green. And we also have some vehicles, so A and B. So the main idea is to focus on modeling pedestrian vehicle interactions. And for that, introduce a measure of risk that the pedestrian uses. And this is used to choose which vehicle to pay attention to. So which one might I need to pay attention to avoid a collision? So this is used to choose the vehicle to pay attention to and to choose whether or not to yield. So say vehicle B is perceived as more risky, and vehicle B is chosen. So if the pedestrian then chooses not to yield, well, they're just modeled as continuing at a desired velocity. But if they do yield, then how much they yield or how they yield is determined with a new and learned vehicle influence function that specifies how much their speed changes based on their proximity to the vehicle that they're paying attention to. So how do we define this model? So we first define the vehicles that the pedestrian might pay attention to. And this is done by examining the longitudinal and lateral coordinate frame of the vehicle. So if the pedestrian is too far away, we'll say that the pedestrian doesn't pay attention. Or if they're behind the vehicle, or in other words, not on a collision course. But this pedestrian is not in the shaded area, so this vehicle is in the pedestrian's attention set. And so in this space, pedestrian may choose to yield, and then how they yield is determined using the vehicle influence function, which is defined next. So this is a learn function to adjust speed. And so this is based on piecewise linear function, linear in the parameters u, with inputs as the lateral distance from the vehicle. So based on this function, the yielding speed is obtained. And this function, its scalar output, just scales the speed of the velocity of the pedestrian. And so the pedestrian's entire movement is given by, if they don't yield, they just continue at their desired velocity. And if they do yield, they continue at this yielding speed. So to describe now the distributions associated with the different quantities, we assume that there's observation noise that is Gaussian distributed, and that desired speed evolves as a random walk without drift, as in other works. And similar to neural networks that are based on self-detention, we treat the risk and tension mechanism. So for the pedestrian choosing which vehicle to pay attention to, this is based on the risk. And it can be thought of as paying attention to the relative risk. And when they choose to yield, this is instead done with just the single risk from that vehicle and can be thought of as the absolute risk. So how this risk is actually calculated is defined next. So it is based on two features, one being the minimum separation distance, which is the minimum distance attained if the pedestrian and the vehicle were to continue at constant velocity. And the second feature used is the time remaining to reach this distance. And so using those to learn are used in a piecewise linear function as at the previous vehicle influence function. But now, how do we actually learn these functions for influence and risk? So now that the model is specified, we look at the likelihood parts in each in turn to see how we might estimate these parameters. And so the first term here, we start with where the pedestrian just chooses the next desired velocity. They then choose, based on the state and the computed risk, which vehicle to pay attention to. And the next is, based on the vehicle that they're paying attention to and its risk, do they decide to yield or not? And then based on this, their movement is specified, they move, and then this is observed noisily. And the remaining terms are weak priors placed to ensure that estimation is well defined. So the bad news here is that this likelihood has many discrete decision variables that could trap an optimization procedure. So as a first step, we want to remove the dependency on the intention variable. So this can be done by only looking at the sets, the attention sets, where there's at most one vehicle. So this can be justified with a pseudo likelihood, and it greatly simplifies our problem, where the remaining sets only have one vehicle or none. So this means that the pedestrian can only possibly pay attention to one vehicle at most. And so this means we no longer have to worry about the attention variable. And based on this, then, if there's no vehicles, we know that the pedestrian will not yield. So this also helps specify additional things. So now splitting likelihood based on these sets, we have information based on that we know the pedestrian will not yield because there's no vehicles. And the second part where there's one vehicle, so they may yield or they may not yield. And so in a stepwise procedure, we can solve for the first part with Kalman smoothing, and the second part with block descent. So this is alternating between calculating the decision to yield based on estimates for the risk function and vehicle influence parameters, and then based on this decision to yield, then estimating those parameters. And these are both standard problems since the vehicle influence and risk functions are linear in their parameters. So these steps greatly simplify the fitting procedure. So now, to evaluate this method, we can test on the DUT campus dataset, which has trajectories collected across a shared space scene and a more traditional marked crosswalk scene. And the other dataset being the IND urban intersection dataset, which has intersections with marked crosswalks. So comparing to other methods, including deep neural networks, we see that with semantic information, one does not generalize well, just because there's so few numbers of scenes that are distinct. Without, it has much better performance. And here, the proposed method outperforms the other methods. And here, we see that the method that didn't do as well before, MEDF, here outperforms SCAN. But the proposed method still outperforms the baselines. So now, to look at some qualitative results, we have the predicted distributions and DUT. And we've observed a trajectory of the pedestrian in green and where they actually walk in orange. And the vehicle is moving with the darker blue is what was observed. So MATF and the proposed method correctly predict the pedestrian actually yields the vehicle. And the proposed method expresses uncertainty over this decision. And in this shared scene example, all methods correctly predict the pedestrian does not yield. And the proposed method captures the uncertainty over this decision. In comparing the speed, the lightweight parameterization allows this method to perform in real time. So from here, we've seen that the proposed risk and vehicle functions help describe pedestrian vehicle interactions without relying on scene features. And this might help the generalization across different scenes. And then for fitting functions, the vehicle influence and the proposed risk to data, the stepwise and pseudo likelihood techniques greatly simplify the process. And we see that the lightweight parameterization helps make inference real time. So in conclusion, this work has led to new and interpretable models of interactions. And the extension, including the extension and generalization car following models, and the development of a novel pedestrian behavior model for shared spaces, and applying that to general spaces. And to apply each of these, also develop more novel fitting and real-time inference procedures to use these methods. And for model building, also developing a simulation framework for fitting models where data may be scarce. So for future directions, 3 main areas stand out, with the first being nominal trajectories. And this makes predictions for autonomous vehicles unique in one aspect, because at the time of making the predictions, the vehicle is planning future actions to take. And since actual future actions will likely affect other people's behavior, these planned actions could potentially be used to make more accurate predictions. For model validation and abnormality detection, we may want to ask, can we detect when a given road user is acting unpredictably? And in these cases, we may want to take additional precautions. So here, leveraging the modeling-based framework may be possible because computing and bounding marginal probability observations under these models is generally easier. And lastly, using weakly labeled data. So high-level intents, such as wanting to merge, are rarely labeled, but can be inferred in some cases. For example, a vehicle we see, we might not know when it actually wants to merge, but at some point, we see that it does merge. So that we can know that at some point in time before it merged, that it did want to merge. So incorporating these weak labels into fitting methods has the potential to broaden the class of models that can be reasonably fit. And I think here I'd like to gratefully acknowledge the support from Ford, which has sponsored my work over the years. And I would like to thank my advisors, Matt and Ram, for being the best advisors I could ever ask for. And also for believing in me when I didn't believe in myself. So it's like the saying of giving a fish to a person, or instead teaching them how to fish. Spending that time to do that. They taught me how to fish, and I found that I enjoy it. For that, I'm very grateful. And to my lab mates in FCAV, Room Lab, Drop Lab, they too have supported me greatly. And I'll miss seeing everyone at the morning working groups, the journal clubs, and the annual testing events like this one. And I'd also like to thank my loving partner, Hitomi, for all of her support. And I'm always learning from her example. 心から感謝しています. And to the rest of my family, thank you for supporting me every step of the way. And thank you to everyone tuning in. I hope you had a good time.